All right. So today's pre-seminar is given by Aaron Kettner, who's going to tell us about an introduction to KMS states on C-star algebras.
Thank you. Yes, that's what I want to do. And let's start from the beginning. So let A be a C-star algebra. So then the state on A is a linear functional. Let's say omega from A to C. So it should be linear and it should be positive. Positive meaning that positive elements get mapped to something non-negative. For all A and plus, the positive cone of the C-star algebra, which is just the set of elements of the form x star x. That's the positive cone. All of those elements should be mapped to something non-zero. Sorry, non-negative. If you don't like C-star algebras, then this positive cone, think of matrices, right? So a positive element is a self-adjoint element with no negative spectrum. So like a self-adjoint matrix with only non-negative eigenvalues. So it should be positive and it should be normalized. Normalized meaning that the unit gets mapped to 1.
So you mean that really not moment.
Oh, sorry. Yeah, I switched. Thank you. And such a state, so this is just, we just demand linearity and then this positivity condition, which is something algebraic, I guess. But such a state is automatically continuous. Yes, so omega is continuous, meaning it's bounded, so it has some operator norm, and in particular, that operator norm will be equal to 1. All right, so that's what the state is.
So implicitly A is a unital C-star algebra. Right?
Now, a particularly important class of states are facial states. This is state omega such that the trace equality holds. So WAB should be equal to WBA. Right, so this is the thing we know from the trace on matrices, that we can commute things inside. And tracial states are super nice, and they're very important in the classification of C-star algebras, but they don't always exist. So there's a lot of C-star algebras that don't have any tracial states. All right, so KMS states are something that is like a variation of this equality, as we will see in a moment. Okay, so before I do that, I need to define KMS states and to define actions by the real numbers. That's let alpha be a map from the real numbers to the automorphisms of C-star algebra. That is an action. So This means that this is a group homomorphism. So post with alpha s is equal to alpha b plus s.
Also consider some type of continuity.
Exactly. So this is we call this strongly continuous. If for all the map sampling T in R to alpha T of A is not continuous. With respect to the norm of A. Now that we have this, we can define what KMS states are. Take a strongly continuous action of the real numbers, so now C-star algebra, and take some real number beta. Then the state omega is called a beta KMS state. For alpha, if the following equality holds, if omega of b alpha I beta of A is equal to omega of AB. Space. For all A and B, where A needs to be entire for alpha. So I mean this equality, right? Omega of B alpha I beta A is equal to omega AB.
But why does it mean I beta?
Exactly. So this looks more or less like this trace equality with this with this alpha of I beta applied to this guy, I guess.
What is I?
Yes, so I is the imaginary unit.
Yeah, but this is on.
Yes. No, I get it there.
Oh,
I get it. Yes, so but what does it mean that we take alpha of I beta? We ask A to be entire for alpha, which means that this function which sends some real number T to alpha T of A, which of course goes from the real numbers to A. This should extend to an entire analytic map from C to A. Okay, so we want this, if we fix A, then we want this map from the real line to A to extend to the whole complex plane and to be analytic everywhere. That's somehow the condition. Those are the elements A for which this equality should be.
And just to remember my complex analysis, entire just means holomorphic on the whole complex plane. Yes.
Yeah, I mean, honestly, to me, this seems a little weird. Like, I don't know why. I still don't have a very good intuition for why this.
This come by physics. This come from physics.
Yes, so that's a good point. So this appears. Originally, it came from quantum statistical mechanics, and I will say a few words about this in a moment. But then it also appeared in Tomita Takezaki's and Kohn's work on von Neumann algebra classification. And nowadays it's also used in C-star algebra classification. I believe Robert will have some project.
Let's make like two small comments, like just to maybe it helps because yeah, I mean this is right, but somehow yeah, if beta is non-zero, actually you get automatically that this omega is also invariant under the action alpha. So this is usually part of the like sometimes part of the definition.
I was going to say this now as a proposition.
Yeah. Okay. Then you can say that, and well, the rest. The second one was about these analytic elements. So it's kind of weird because you'd be like, why do you even have such a thing? But they are actually dense in the system algebra. For instance, the set of analytic elements will be dense in your system algebra.
Analytic elements are those where this map extends.
Yes.
So if you take out the T.
So you have loads of them, and really what you do, like if you remember some complex analysis, is like you smoothify it. So you kind of integrate this alpha like over alpha t, and then with some kind of like kernels, like a Fourier series, and that integral will give you like a thing that's close to alpha, and that's so you have lots of this. That's common.
So but just to make sure I got you in the first point, in the definition, you want to assume that omega is invariant under the action. Maybe.
That's sometimes assumed, and it's redundant, I think, if beta is not zero, but if beta is zero, you actually need to assume.
Got it. Okay.
But
so just finish that sentence. And now, yes, so the proposition, this is proof, for example, in Bertelli-Robinson, is that if omega is a KMS state, for alpha, and you choose beta to be non-zero. Because, okay, I should have said this, but if beta is equal to 0, then this alpha of 0 of A is just A, right? Which means that you get exactly the trace. So a KMS state for beta equals 0 is just the trace. Okay, so for all beta except 0, we have that omega is automatically alpha invariant. Which just means that if I decompose omega with alpha t, this is the same as omega of t. Right. Okay. I just wanted to make it, before I move on to the main example, which is the Kunstalgebra, I wanted to make a small aside about where this comes from in physics. So in quantum statistical mechanics, your A, the C-star algebra, is the observable algebra. Of your physical system, meaning that each self-adjoint element in here gives you some quantity you can measure, like position, momentum, energy. Any such quantity will have an associated element, self-adjoint element in the C-star algebra. And then the state on A is an actual state of your system. So something that tells you how your physical system looks like, where all the atoms are, how fast they're moving, if they're spin up or spin down, right? It seems like the conference is too. And then our strongly continuous action is the time evolution. That's why it's the linear, right? It's like the passage of time. It encodes how your system evolves with time. And KMS state, the Gustav KMS state, is an equilibrium state. At the temperature, which is proportional to the inverse of theta, so it's like 1 over Boltzmann's constant times theta. That's why sometimes beta is called the inverse temperature. So it's an equilibrium state, which means that nothing happens anymore, right? Like if you mix milk into your coffee, then the equilibrium state would be when you can't see anything happening anymore. It's like a homogeneous mixture. And this fits with what we found here, right? Like if I'm in an equilibrium state, nothing should happen as I evolve in time. So the state should certainly be invariant under the time. Yeah, so that's where all of this comes from. Yeah, and for finite systems, you always have a unique equilibrium state at a given temperature, but for infinite systems, not anymore. So you can have like very interesting structure in scripts. But are there any questions so far?
Are there any theories about, like you said before, tracer states don't always exist on C-strata, but are there theories about when you have KMS states on C-strata?
I don't know if there's like a general existence, right? Like you can certainly, for specific C-algebras, you can study the KMS.
Yeah,
the donut traces.
that's essentially what I don't talk about. But yeah, it's a good question.
But I guess it's not just a C-strata, but you also have to have an action of the real numbers on that C-strata.
Yeah, right.
So the existence of KMS, I guess.
But I mean,
yeah, I'm just
the existence of the actions, that's what there exists in KMS.
Yeah.
Right.
Okay, so this actually fits nicely with the next topic. So now the remaining time, which I'm not sure how much actually that is because I don't know when we started exactly, but I want to discuss the Grundsearch processing. Okay, so
I'd say you have 13 minutes, I'd say 13, 14 minutes.
okay. Okay, so what are the Grundsearch algebras? I'm going to start with the second one, O2. Let O2 be the C-star algebra generated by two elements, S1 and S2, with the relations okay, what are the relations? First of all, we want both S1 and S2 to be isometries. So we want S1 star S1 to be equal to S2 star S2 to be equal to 1. And secondly, we want S1 star plus S2 star to be also equal to 1. Okay, if you attended the Mali we had a few weeks ago on graph C-star algebras, this might look vaguely familiar to you, right? And in fact, O2 is the graph C-star algebra associated to the graph that has one vertex and two loops. Right, so each edge, you have two edges which are over the same vertex. Each edge gives you a partial isometry. In this case, it's going to be an actual isometry because we only have one vertex, and then the sum over the range projections needs to be the identity as well. Okay, and more generally, the algebra ON for n natural number is generated by elements S1 to Sn, such that, well, basically the same thing. So Si star Si should be equal to 1 I pi. And the sum over all the sum over all Si star is also. And this corresponds to the graph system algebra that has one of the graph that has one vertex and n loops. And edges over that vertex.
This O1 is just
Or one, I guess.
Oh, one is just continuous functions of the circle. It's generated by one again.
yeah.
Okay, and it's very easy actually to see that these const algebras don't have traces. Okay, they are very important in the classification program. They have this property which is called purely infinite. They're simple and purely infinite. In particular, they don't have traces, and it's really easy to see because let's say omega is a trace. Let's just say O2. Then what is omega of S1 star plus S2 S2 star? Well, this guy is equal to 1, right? So this is 1. But on the other hand, we can split up the sum using linearity. And now we can swap those because of the trace equality. So this is S1 star S1 plus omega of S2 star S2. Each of those guys is equal to 1. So you get 1 plus 1 equals 2. So we just prove that 1 equals 2, which means you have the traces. Okay, just going to erase this again. Okay, now as Misha pointed out, for KMS states, we don't only need a C-star algebra, we also need an action of the real numbers. So what's our action? There is a strongly continuous action of R on or two given on the generators by what do we want to do? So alpha t of S1 should be equal to e to the minus t S1, and alpha t of S2 would be the exact same thing. It's just e to the t S2. Right, so we just take the generators and we multiply them with the complex number of modulus 1. And of course, you have to show that this is well defined, that this really gives you an action on the C-star algebra, which it does because it respects the relations. And
this is the gauge action from the graph.
And this is the gauge action, exactly. So this is called the gauge action. Right, you could also regard this as an action of the circle, but now in our setting, we want to regard it as an action of the numbers. Okay, and now comes the last thing I want to mention, which is the theorem. The gauge action on O2. And I'm talking about O2, but of course, all of this would work also for ON. I just wanted to pick one particular example. So let's just say in brackets, ON has a unique KMS state. At beta equals to the logarithm of 2, or in general for ON, it would be the logarithm beta equals the logarithm of n. Okay. And I just want to very quickly, I don't want to prove this, but I wanted to show you how to get to this inverse temperature, because it's kind of cool. It's the exact calculation I just did for traces. So, okay, what did we do? So prove that it's not a proof. So let's say omega is beta KMS state for some beta. Okay. Then we just do the same thing we just did, and we see, okay, what happens if we plug in S1 star plus S2 star. Right, so this is again equal to 1, of course. Now we can do the same trick as before. S1 star plus S2 star. But now we can't just swap them because we don't have this equality anymore. Instead, we have this equality. So this is going to be omega of. So which direction is this now? So start here, put this here, so this is S1 star beta S1 plus omega of S, right, now what is this? What is this? This is e to the I beta S1, so just e to the minus beta S1, just by definition of the gauge action, right? And here it's the same thing. So this whole guy is equal to e to the minus beta of S1 star S1 plus e to the minus beta omega of S2 star S2. Now again, those two guys are equal to 1 because we are talking about asymmetries. So this is just equal to 2 e to the minus beta, right? Which means that beta is equal to log. So of course, this doesn't prove existence or uniqueness, but it does prove that if we had a KMS state, it has to be a temperature log 2. Just because of these simple relations. And actually, I mean, the proof is not very difficult. You can just again play around with the generators. And you can see, okay, if I have this generator, then any KMS state would have to have this value on it, and then see it's unique, and then you show it's well defined also. So yeah, that's the proof. So yeah, I guess that's it.
Thanks, Aaron. Anybody have any questions?
That was a very general question. Were you interested in KMS? What they say about the system? For example, about the traces, okay, you know, this is some things about the structures, but about KMS.
I think Robert is the more qualified.
I mean, there's some structure. I mean, even traces don't tell you that much, I would say.
Okay. Okay, for example, for the traces, it says that I think that exists as an underlying trace implies activities. or mobility implies I want to go
Yes.
yes. And what about for the groups is algebra? It says that existence of the
Yeah. I mean, here the problem is somehow that, yeah, they depend on this flow alpha, and then you can change it and you get different, and then you can pretty much get anything. That's kind of so. It's more like, I think, it's more they give information about the action if you want. That's more, I think, how you should think about that.
okay.
But you know, if you want, like, if you know that you have 0 PMS states, for example, then you have traces. So that's something, I guess, if you want structure. But I think it's more like these states give you information about the action,
Okay.
which gives you information about the algebra. But
Oh, so we should think like the.
it's more a property of the action. I think that's.
And okay, and then what type of the properties of actions we are to understand?
Like, I think so for example, the one thing that, I mean, this is not obvious, but for example, if you have such an action and you have a KMS state, then this will give you a trace, not on A, but on the cross product with the real numbers.
Okay.
So something like this, right? So if you take the cross product A with R, and any KMS state will induce you some kind of trace on the cross product. There's not, yeah, it's one of these like unbounded traces, right? It's not, so that's something, but it wouldn't really, give you that if you have KMS states, you have some sort of property. It's more like if you're trying to compare two actions, you're trying to understand whether they are the same, then you might look at KMS states because they should.
For example, the actions of R are false means that, for example, if they are both conjugate or still no something else.
Yeah, so if two actions are cocycle conjugate, then the set of KMS states are isomorphic, like in some sense.
Okay.
Isomorphic in this category, yeah. So that's.
Maybe we should finish up in the minutes of the room.
Yep, okay.
Sorry.
All right, so thanks again, Aaron.